Can you see the slides? Anybody? Can you please confirm?
Yes, sir.
Yes, sir.
Thank you. Thank you. Okay. So we have built on this set partial ordered set structure, and we had proceeded up to the definition of lattices. We have defined several properties that holds on lattices, several properties of the meet and join that holds on lattices. So you try to remember these properties. These are the commutativity, associativity, absorption, idempotence. One operation was still missing, which is the complement. So to do that, we need to define what is called a bounded lattice, and you have a maximum element 1 and a minimum element 0. And we have shown every lattice is bounded. Then we consider another property, which is distributive lattice, where this distribution law holds, and then we have seen that some of the well-behaved lattices are distributive. And then we defined, moment we defined maximum and minimum, we defined that in a bounded lattice, of course, it has to be bounded, otherwise we don't have the maxima and minima. We defined the notion of complement. So X and Z are complement if the meet of X and Z is 0 and the join of X and Z is 1. And we have seen that in any bounded complement lattice, every element will have a complement. Every element, if it is bounded, that is, there is a maximum and a minimum. For every element X, you can define a complement Z. We'll usually denote the complement by this X bar. So complement of X is X bar. We'll denote by this, the usual definition. Okay. So if in addition to this bounded lattice, so any bounded lattice, every element will have a complement. In addition, if we have the distributive property, which we defined here, this is the distributive property. So basically nothing, the usual the meet distributes the join. So if you have this distributive property, then not only every element will have a complement X bar, and the complement will be unique. Every element will have a unique complement. Say, I think in these lattices, these bounded lattices, they have a 0 and 1. You have seen the complement was not unique. For example, can you tell what is in the third lattice, in the bottom third lattice, what is the complement? What are the complements of E? What are the complements of the element E?
C.
C is a complement. And what is the complement of A?
Again C.
Again C. Okay. And let us look at this lattice, the first one. So you have 0, 1 and A, B and C. So what is the complement of A?
B and C.
B and C. So it's not unique. Right. So you can have a unique complement and you may not have any unique complement. But we will prove that if your lattice is distributive, that means these two properties are valid for every element X, Y, Z, then if the complement has to be only one, it has to be unique complement. Let us prove that. Okay. So let X be an element, any element, and let it have two complement. X bar is one complement and Z is another complement. We'll show that this cannot happen. Okay, so let us go this way. So X bar by this definition of bounded lattice is X bar meet 1. 1 is the maximum element. X bar meet 1. Okay, by the definition of definition of bounded lattice. Wait. Why is this true? Can you tell? Why can I write X bar equal to X bar meet 1?
Because X bar bar is
So 1 is the maximum element.
Yes. So
x bar is less than 1. So
okay.
intersection.
All right. Very good. Very good. It's the because it's the maximum element. Okay. And then since x and z are complements, since x and z are complement, we have assumed. So x join z is 1. So I replace 1 by x join z. Okay. So now x bar, since x and x bar are complement. Wait a minute. Okay, all right. So now apply the distributivity property. Okay, it's a distributive lattice. So apply the distributive property on this. So you get that is equal to x bar meet x join x bar meet z. I'm just distributing this join over this meet. I'm just distributing. So I get this. Okay. And so again, by definition, since x bar is a complement of x bar meet x will be 0. X bar meet x will be 0, and this is like this. Okay, so now again by the same property, since 0 is the minimum, I can replace 0 by x meet z. I can replace 0 by x meet z. Why can I do it? Why can I replace 0 by x meet z? Can you tell?
So
Why?
property of complement.
Property of complement. So I have also assumed that z is a complement of x. I have assumed z is a complement of x. Okay, so I replace 0 by this. So this becomes this thing. And this, what I have is that I again apply distributive property. So I get this. So I get this. Okay, so x join x bar meet z. So x bar is equal to this now. And since x and x bar are complement, so x join x bar will be 1. So you have 1 meet z. And since 1 is the maximum, 1 meet z is z. So x bar and z, they are complement of each other. Sorry, they are the same. Sorry. They are the same. So we have proved that x bar and z are the same. So any element x can have only one unique complement if it is distributive. And of course, it has to be bounded because otherwise you cannot define a complement. Okay, now let us see. So among these three lattices, which two are distributive lattice? Can you tell which two are distributive lattice? Which two are distributive lattice? First one, is it a
So the first one is not
No, sir.
distributive.
Why
The
it
first
is
one
not
is not
distributive?
distributive.
Why did you say?
So
it is
C
not-
has two complements.
C has two complement. Very good. So there has to be only one complement. Okay. So what about this chain 0A 0 B C A 1? What about this chain? Is it distributive? Does every
No,
element
sir.
have a? Huh?
No.
Why no? Why no?
So like what will be the complement of A, sir? Like
Yes. What is the
The second
complement
one is
of
not
A?
a complementary lattice.
Second one is not a. What is the complement of A?
sir, means it
Does it
will not be
exist?
there.
It is
No,
not
sir.
there. It is
Yes.
not there. There is no complement. So it's not a bounded lattice. Sorry, it's a bounded lattice. It's not a complemented lattice. Oh,
Yes.
okay. Wait. But I have a confusion. Okay, no. Okay, so bounded lattice need not be complemented lattice. All right. So now let us look at this nice structure, the third one. So it's the third one. And so basically these elements, we could have named them as D, E, F, but they are basically A join B, A join C. Sorry, A meet A join B, A join C, B join C. I could have named them with other element also. Okay, so is it distributive? Does every element has an unique complement? What is the complement of A A join
Sir, B union C.
B union C is a complement of A join C. Right. What is the
A,
complement?
sir.
Wait. Why is it complement of A? Yeah, it's the complement of A. B union C is the complement of A. Okay. What is the complement of C?
A join
A
B.
join B.
Okay. What is the complement of B?
A join C.
A join
A
C.
join C. A join C. Huh. Okay. So every and complement of 0 is 1, complement of 1 is 0. So you can see every acha, you have also seen that there are unique complements. You have only one complement for every element. In fact, you could have noticed a structure. If you imagine this as a cube, you see diagonally opposite corners are complements of each other. The diagonally opposite corners, they are complement of each other. Okay. So this is distributive, this is bounded, this is complemented. So it has all these three properties. So you see, one thing you see, the moment all these three properties hold, that it is bounded, it is complemented, and it is distributive, these three properties hold on a lattice, then you can see some kind of a nice structure. You can see some kind of a nice structure. Okay. All right. So these three properties are important. We will see later. These are important for our course also. Okay, so these lattices, which are bounded, which are complemented, and which are distributive, would be called a Boolean lattice. Would be called a Boolean lattice. So Boolean lattice is a bounded, complemented, distributive lattice. Bounded,
Sir.
yeah.
Sir, can you please move to the previous slide? Sir, if a lattice, if all the elements have one complement, but it is the same element, it is
That's not a problem.
okay. Okay.
So one element cannot have two complements.
Okay, sir.
None of the elements should have the complement should be unique. It's possible that multiple elements have the same complement. That's possible. Okay. All right. So okay, fine. So we would call this as Boolean lattices. We'll call this as Boolean, and this is this is a very beautiful symmetric structure. We'll see, and this symmetry has many implications in terms of the circuit realization in Boolean algebra that we usually do. So this structure can be very well used to represent usual Boolean algebra structure. Okay, so let me go to the definitions one more. So there are it's bounded. There is a max which is 1 and min which we call 0. The distributivity holds, which implies that so the first two, in fact, complemented should have been added. Every element has a complement. The first two implies the next two. So if the first two holds, we have already proved that it will, by as a corollary, have a unique complement. There is now another important structure which will hold in Boolean lattice. We'll see, which is called the De Morgan's law. Okay. The De Morgan's law is a principle of duality. I'll try to explain what it is. What it means is that kind of, you see, you look at the third lattice. You look at the third lattice and you kind of overturn it. That means, what should I say? You reflect it along the horizontal line. You reflect it along the horizon. Imagine this as a cube. You have placed the cube in certain one, resting it on the 0. 0 is at the bottom, 1 is at the top. You invert it. You just reflect it along the horizontal axis. So what happens? So what so now look at the next structure. And the next structure I can think of as if I replace all the 1 by 0. I replace the 1 by 0 and vice versa, and replace all the meet by the joins. So this 1 and 0 and meet and join. So 1 and 0 are two elements, and meet and join are two operations. I will interchange them. I will interchange the maximum and minimum element, and I will interchange the meet with the join. If I do that, you will see if you invert the lattice, if you how should I say, if you invert the lattice and give the 1 to the bottom and 0 to the top, which is equivalent to replacing 1 by 0 and mid by join, you get the same structure. It's still symmetric. That means it is symmetric with respect to this substitution of 1 by 0 and mid by join. It's symmetric. It still looks the same. It's the same lattice. So this is called the duality principle. So 1 and 0 are duals of each other, and meet and join are duals of each other. So these two are dual pairs. And if you replace the dual, you have to replace both. You cannot just replace 1 and 0 and keep the meet and join as it is. You have to substitute both with each other. Then it's still a Boolean lattice. It's still a structure. It's unchanged. It's still a symmetry. This symmetry is there. Okay. And since this symmetry is there, all this distributivity, associativity, everything will still hold. If it holds with say maybe one assignment of 1 0 and one use of meet, it will also hold for the dual. All this associativity, absorption, everything will hold for the dual too. So this is known as the principle of duality. Principle of duality, which means any of the rules that which basically means this, any of the rules that we talked about, you see this and this. I am writing two rules every time. So one is nothing but the dual of the other. I have replaced the meet by the join. So meet and join are duals. 1 and 0 are duals. There is another self dual, which is the complement operation, because now we are also talking of complement. Complement is self dual. Which means that you have to replace x by its complement. If in any of the law the complement appears, you have to replace x by its complement. So those are sometimes called self duals. Okay. So this duality principle of meet, join, complement, and max min elements is called the De Morgan's law. It's called the De Morgan's law. Okay, so you know very well. So x meet y complement is x complement join y complement. So I am just doing the reverse. I'm just doing the reverse. Okay, and similarly this other form. So this is called this arises from the duality, the symmetry of the distributed lattice. It arises from the symmetry of the distributed lattice. Okay, so these are actually easy to see that this holds. So basically the old thing that the meet of the complements is 0, which is the definition of the complement. So meet of the complements is 0. Similarly, you have the definition that join of the complement is 1. Join of the complements is 1. Okay. So can you tell me how does the first De Morgan law follow from this? Can you tell me how does the forget about this first? How does the first De Morgan law follow from these 3 steps? Anybody? Anybody? Why this is a proof of the first De Morgan's law?
Sir, meet is intersection of sets and means. Sir, in which way we have to say that it is correct?
Yeah.
Like,
So let us look like this. So what is the De Morgan's first law? What is the De Morgan's first law? So if we say that x join y, the left hand side without the complement, is a complement of the right hand side, then we have proved the first law. So just remove the top bar for the left hand side of the first law. Okay, and if we so which is this? Which is x join y? X meet y, which is x meet y. Okay, so if we show this left hand side without the complement, and the right hand side as it is are complement of each other, then the first law is valid. Agreed or not? Agreed or not? If we show that the left hand side without the complement and the right hand side as it is are complement of each other, then we can write down this identity. Isn't it so? Agree or not? Or okay, maybe.
Yes, sir.
Okay.
So then we need to show the union the join also, that join should be 1.
That I'll show. That I'm next showing. Okay, first let us look at this. Yeah, join also you should show. Join also you should. So that's what I'm doing. I'm taking the left hand side without the complement and taking the right hand side, and their meet should be equal to 0. Their meet should be equal to 0, and I proved their meet is equal to 0. Now I'll prove the other one. So both I have to prove. You are very right. We have to prove both. Let us prove the other one. Let us prove the other one. So their join should be equal to 1. So let's take the left hand side without the complement and the right hand side as it is. Let us try to join them. Let us try to join them. I apply the distributivity, associativity, everything, and we show that it is equal to 1. Okay, we show that it is equal to 1. So I have proved successfully that the left hand side without the complement and the right hand side are both complement of each other, which means the first law is valid. Is it okay? Or I am missing something? So how do you prove the second law? How do you prove the second law? How do you prove the second law? Give me the statements, the 2 statements that will prove the second law.
Then we will find the complement for x join y.
X and y, and we'll show that x and y and
Yes,
what
sir.
else is
The
X
meet
join
of
y and complement of x meet with complement of y are complements of each other.
very good. So basically we'll prove that these two elements, if we take their meet, it is 0. If you take their join, it is 1. That will prove. In fact, it will be very easy to prove. I think you can apply this. So in any proof that we are doing, what you do is that, so these are the basic things, that this commutativity, associativity, absorption can be proved from the others. Idempotence can also be proved. Commutativity, associativity, and the existence of the complement. Okay, the definition of the complement. So if you do this, you successively go on applying those. And you prove it. Okay, I think this is simple. This is it's almost trivial. Okay, so let us go ahead. All right. Before that, I think let us take some definition examples. Just take some example. These are 2 examples of Boolean lattice. You can see all these property, that they are a lattice, they are a distributive lattice, they are a bounded lattice, there is a maximum and minimum element. Okay, and they are complemented. So everything is satisfied for both these 2. So both these 2 are Boolean lattices. So can you tell what is the left hand lattice? What I am looking at? It's a power set. So I'm taking a set containing 3 elements A, B, C, and all other elements of the power set of the lattice are subsets of this. So it's the power set. All the elements of power set of ABC are the elements of this lattice. And the right hand side, I am taking bit vectors of length 3. I am coming to this. I have written down the bit vector somewhere. I'm coming to that. Acha, so in the left hand power set, can you tell what is the partial order relation? What is
Subset.
the subset? Inclusiveness is the subset. Acha, why is it a distributive lattice? Why is it distributive, and other things I think is obvious. Why it is distributive? Can you tell? First of all, you can verify that this is a lattice. I think that's obvious now. You take any two element, it will have a meet and a join. What is the maximum element? Maximum element is the full set ABC, and the minimum element is the null set. And inclusiveness, as you have said, is the partial order relation. So why is it a distributive lattice? Just one line, can you tell? No need to argue anything. Just look at the property of the partial order of the relation. Why is it distributive?
Sir, I had a question in
Yeah.
one of the previous statements. Sir, you said that if the complement is so if a lattice is distributive, then its complement is unique. Sir,
Yeah.
does the reverse also hold true? Like if complement is unique for all element, is it guaranteed to be a distributive lattice?
I am coming to that. I am
No,
coming to it. It's a very
can I
good
just-
question.
can I-
It's
can I
a
just- Can I
yeah.
just
Please.
comment?
Please.
See, the statement was that in a complemented lattice, if a distributive lattice is complemented, then the complements are unique. Or rather, if a complemented lattice is distributive, then the complements are unique. It is that way. It's not a standalone property. If
Okay,
a
sir.
yeah, okay, yeah. In fact, that is that's how the proof was done. If you look at it.
Acha, can you
Yes,
tell
yes.
one more? Can you tell one more thing in this power set lattice? What are the meet and join operation in terms of set operations?
Intersection and union.
Intersection and union. And so that is, I think it is easy to argue that it is a distributive lattice because usual set intersection union are distributive. Intersection distributes union, union distributes intersection. Okay, so they are distributive. So naturally this will also be distributive. So this is an example of a distributive lattice. The right hand side, can you tell? So I am telling you this is a distributive lattice, and this 0, 0, 0 is the minimum element, 1, 1, 1 is the maximum element. Can you tell what is the meet and join operation here?
Bitwise AND and bitwise OR.
Yes, bitwise AND is the meet operation, bitwise OR is the join up. Can you tell what is the partial order relation here in the bit vector Boolean lattice? What is the partial order relation?
A number is a submask of another number.
What is the meaning of submask?
So all the zeros are zeros, but some of the ones can be zeros.
Okay.
A is a submask of B if all the zeros in A are also zeros in B.
Yeah,
And some
you
of
are,
the ones.
You are correct. So let me put it in this way. That A is less than equal to B if A is less than equal to B if the join of A and B is B. Are these two definitions equivalent? A is less than, let me write it down, wait. Let me write it down.
So we can say that A is less than B if the number of ones in A is less than number of ones in B.
Okay,
No,
but
that is not correct. That is not correct. You have to compare them position wise, and in each position, either those are identical or one element, the so-called lesser element must have a 0 while they are with respect to the other element.
So this is true for every lattice now. I mean the condition you wrote.
Yes, sir.
No, you consider it bitwise. If you're looking at the lattice on the right hand side, you consider the bit position. So either the values are equal, or I mean for an element to be less than or equal, in this case it is less than. So the lower element will have a 0, upper element will have a 1. That is the relation.
so CRM, can we write this?
No, you'll have to look at it. It's best to look at it bitwise, no?
Okay. Yeah, so now what I'm saying is that are these two equivalent? That means if I define the relation like this, A is less than equal to B, if and only if A equals join of A and B. A equals A and B, where A and is the bitwise and B equals A or B. So let us see if this is verified. So 0, 0, 0 and 0, 1, 0 is 0, 0, 0 less than equal to 0, 1, 0.
Yes, sir.
Yes.
Yes, sir.
Yes. Take anything else, 0, 0, 1 and 1, 0, 1. Does the first rule hold?
Yes, sir.
Sir, these are the bitwise operators, no, sir?
These
A
are
and
bitwise
B and
operators.
A. Okay, sir.
Bitwise operator. So this is, I can write it as this: A equal to A, bitwise and bitwise and B. Okay, then so does this hold?
Yes,
Yes,
sir.
So, okay, so this is I call it relation 1. Now I define relation 2 this way. I define relation 2 this way. That this is another relation. I'll say A is less than equal to B according to R2. Now R2 is defined this way. A is less than B if the B is equal to bitwise or A or B. So this is rule 2. B equal to A bit or B. Then this is another relation I am defining. Okay, so this relation, does it hold in this lattice?
yes, sir.
Okay, so these two relations are equivalent. So you see, both these relations, under both these relations, these are Boolean lattices. So there is again a symmetry. You can use either R1
Sir,
or
what
you
is the
can
relation between 0, 0, 1 and 1, 1, 0?
0, 0, 1 according to R1 or according to R2?
Sir, according to anyone.
Okay, 0, 0, 1 and
1,
repeat
1,
again.
0.
That those will not be related, right?
So that is not related. We have not drawn any relation between them. I don't have this less than equal to between them.
But you can define meet or join of those. Those are not related, but you can define meet or
Yeah,
join.
that can be defined. You can still define a meet and join.
Okay, sir.
You can still define a meet on a join. Okay, so see, so now what we have in effect, what we have done so far, we have defined partial ordered sets, then we have defined lattices, we have defined bounded lattices, we have defined complemented lattices, and we have defined distributive lattices, and then we have come up with this nice structure. So a nice structure. So there is another way you can define such a nice structure, and these are equivalent, and that's by way of something called an algebraic structure. So what is the algebra? So far we have only dealt with these partial order sets and relations and distributiveness and all these things. There is a completely alternate way of describing the same thing. So this power set or bit vectors, there's a completely alternate way which is consistent with what you have done, which is called an algebraic structure. So what is an algebraic structure? Algebraic structure is a combination of three things. It's a combination of a set A, sometimes called an underlying set or a carrier set or a domain. So can you tell what is the set for the things you have considered? Maybe all the subsets, these are sets. It's a set. The power set is a set. All big vectors of certain length n is a set. So this we'll call the underlying set. And then we have a set of operations. So this is a general definition of algebraic structure. We'll see what is a Boolean algebraic structure as a special case of this. And then we have a set of operations, say of finite arity, typically binary operations. So these operations can be like plus or dot or conjunction or disjunction or anything, union, intersection. You can have any operation between the set elements. So this is the second thing you have to do. And then on this set, based on these operations, you have a set of axioms which are nothing but identities, like the De Morgan's law. These are set of identities. And these operations must satisfy these axioms. Okay, so you whatever we have defined so far using this lattice and distributive lattice, the same thing we can describe as an algebraic structure. We'll call it a Boolean algebra. And these two are equivalent definitions. These are just two ways of defining the same thing. One is by means of lattice and one is by means of and set operation axioms. Set operation. So can you tell me this definition of Boolean lattice, if we call the corresponding algebraic structure as Boolean algebra, what is the set? For example, take this bit vector. What is the set? What is the underlying set? Anybody? What is the underlying set?
0, 1 to the power 3.
0, 1 to the power 3. And what is the binary? What are the operators? Binary or unary? What are the operators? By the way, one interesting thing you note in this bit vector lattice is that the complements are again diagonals. So these are nothing but bitwise complements. You take 0, 0, 1 and 1, 1, 0, they are diagonals and they are just bitwise complement of each other. Okay, so what are the operations in this if we consider the equivalent Boolean algebra? What are the operations? Can you tell?
Less than or equal to and meet and join and
no.
complement.
What operation means? What operation means? Okay, let me clarify it this way. It's closed under this operation. That means you take two elements of A, you join them by a operator, and the result you get is also a member of A. It should be closed under this operation. So for example, if A is element of A and B is an element of A, then let's say one operation, let me call it a plus operation, then A plus B is also an element of A. Similarly, if we have another operation, dot operation, then A dot B is also an element of A. So it is closed under these operators. Only then you call them as operators.
Bitwise and or and complement.
Very good. So so we have three operators, two binary operators. One is bitwise and, one is bitwise or, and the other is the complement, bitwise bit complement, flipping the things. Okay, so this forms a nice structure.
So the absolute value of the difference will also be the operation.
No, what is difference? I have not defined anything called difference yet. I have only defined this bitwise and bitwise or. Okay, so you want to bring a third operator? You want to bring a third operator?
Yes, sir.
Okay,
that
what
will
is the
also be
operator?
derived from this.
Yeah, that may be derived from this, but okay, as such we'll consider it as a third, as a separate operator. We see, you have to be, we are just talking about two operators. Let's say I name them as plus operator and the dot operator. Achha, tell me one thing.
Okay, sir.
Tell me one thing. All these distributive, so if we have defined the plus and dot this way in our algebraic structure, does all this, okay, let us come to the third part then. Okay, so these are the operator. What are the axioms on this Boolean algebra that will hold for this bitwise and bitwise or? What are the axioms? What are the identities that will hold involving these operators? Can anybody tell? That I am trying to, so somebody has defined me this Boolean lattice. I am not happy with, I don't like this lattice representation. I like algebraic representation. I like algebraic structure. So I have to define the equivalent algebraic structure. Okay, and I have defined the underlying set. I have defined the operation. Now I have to define the axioms. So can you tell me what are the axioms that will make these two equivalent?
Sir, commutativity, associativity, distributivity.
Yes, it is exactly this. it is exactly these axioms plus the De Morgan's law because of the distributivity. It is these axioms. In fact, absorption is not an axiom. Absorption is not an axiom. So commutativity, associativity plus the De Morgan's law, which comes from the complement, the duality of the complement, plus the De Morgan's law. So these are the axioms of the algebraic structure. So if you have an algebraic structure consisting of an underlying set of bit vectors, operations being bitwise OR, bitwise AND, bitwise complement, and if you go by this associativity, commutativity, and De Morgan's law, these as the axioms, then the Boolean lattice and the Boolean algebra are one and the same. Every property that you find here will have an equivalent property in the algebraic description. They are one and the same. You might wonder that why we have taken all this complicated route to describe such simple things. Why we have taken so many definitions over 2 weeks and such. So the thing is that these are very general structures. These are very general structures. And even though for the particular case of Boolean algebra circuit that you will deal with, maybe so much is not required, but you can extend this structure to other. For example, there is a I think it should be interesting to you. So we have talked about this Boolean lattice. So the reason it is so popular is that all the digital circuits are based on these logic gates and OR, so they are nothing but operators in this Boolean algebra and so on. So recently you must have heard there are things like a quantum bit, a qubit. So the good thing is that you can define a similar algebraic structure or similar lattice structure over quantum bits with just the definition of meet and join changing, depending on or the operators of algebra changing, because the quantum operators, why these Boolean algebra operators are popular? Because we had logic gates which can easily implement it. Then there are equivalent quantum gates which implement alternate operations. But the abstract part is that they also follow this kind of lattice structure. They also follow this kind of algebraic structure. Okay, it's just that the operations are different because of the hardware involved. The operations are different. But still, you can have similar structure there. You can have similar expressions, logic minimization, everything you can have in a quantum system, if so possible. So that's the good part. So if you are asked to generalize beyond a usual 0-1 logic system to more general systems, you can just simply extend this structure. I don't know, maybe I'll give you some pointers. There's a nice algebra you can form about qubits or quantum bits, which are equivalent. You have a similar structure. Okay, all right. So, but anyway, let us go ahead. To one more observation. You see that there are some elements in this Boolean lattice structure. Achha, one more small point I'll just quickly mention is that you see there is a kind of isomorphism, so to say, between this bit vector lattice and the power set lattice. There's a kind of isomorphism. They look the same. What isomorphism means that every element here will have an image in the other lattice. So for example, this 0, 1, 1 can be mapped to BC. To AB. There's a 1-to-1 correspondence between the elements, and all the other relations, if they hold between the original pre-images, they will also hold in the images. If you map one to the other, if they hold in the pre-images, they will also hold in the images. So that's a isomorphism. And the reverse is also true. So the inverse is, so if from say this bit vector to power set, if you have a 1-to-1 mapping, and then if there is a relation between two elements here, there is also a relation, we call it homomorphic. And if it is homomorphic both ways, you call it isomorphic. So there's isomorphism. We'll later see that not all Boolean lattices, some special types of Boolean lattices are all isomorphic to each other and all isomorphic to this power set and bit vector. So any Boolean lattice, of course, a particular category, not all Boolean lattice. I just give a rejoinder. Not all Boolean lattice. Most of the Boolean lattices look like or are isomorphic to these two structure, this cube-like structure, the power set and the bit vector set. Okay, so we'll, but not all. I mean, just to I warn you. Okay, but you see there are some special elements here. So what is special about this A, B, C? They are very close to the null. What is special about this 0, 0, 1, 0, 1, 0, 1, 1, 0? They are just Hamming distance 1 from the minima. They are all Hamming distance 1 from the minima. Okay, and this A, B, C are just cardinality is just 1 more from the minima. Okay, so there are these special elements besides the 0 element. The 0 element and the min and the max element are special. We have already seen they are special, but there is some other special elements in the sense that you can sort of compose the other elements based on these lowermost elements. These are kind of these are others can be expressed in terms of this. So they can be combined. They are like bases which can be combined to do this. So we'll see, and we'll give a special name to them. We'll give a special name to them. How much time do we have? Anyway. Okay. So for that we'll need 2 more definition. Let me quickly do that. Okay. Suppose script A be a lattice with a minimum 0. So any element small a will be join irreducible. Will be join irreducible if if you have 2 elements x and y, both of which are less than equal a, you have 2 elements x and y, both of which are less than equal to a, then a is not equal to their join. So let's say x is b1, x is b2, y is b2. So is 0, so what are the join irreducible element? Let's take, okay, let's take 1 by 1. Let's take 0. Is it join irreducible? Is 0 join irreducible? What are the x and y's which are greater than equal to a or greater than equal to 0? Anybody? I think let us stop today. We'll do it in the next class.
So we should take x and y less than equal to 0 if we want to find.
So see we'll do it this way. We'll take so let's say a be any element of this lattice. We want to prove that, so this join irreducible is a property of an element. It's a property of an element. So if I want to see if this property holds for an element, what I will do is I'll take all the x and y which are greater than equal to a. All pairs x and y which are greater than. So take all the elements which are greater than equal to a and take every pair of them. And if the join of these 2 elements x and y are different from a, then a is join irreducible for all x, y. Okay, I think that the equivalent
x, y are greater than 1?
X and y are greater than equal to, less than equal to a. X and y are less than equal to a. So for example here, or okay, maybe let us take this equivalent definition which is easier to visualize. So if a is equal to a join xy, then a is either x or y. So if we find a which is the join of any 2 elements x and y, then a must be either x or y. Either x or y. Okay, so let us take this. So in the first lattice 0 and a. Okay, so is 0 join irreducible?
Yes, sir.
Is a join irreducible?
No, sir.
Why?
Oh, okay, sir. Yes, there is or. Yes, sir.
So next, let's take the second lattice. Is 0. In fact, I think one thing you have already figured out is that 0 is always join irreducible, because if you take if 0 is the join of two sets, then the one of them has to be 0. Okay, so 0 is always join irreducible. Let us look at the second lattice B1. Is B1 join irreducible? Is
Sir, in the first
Yes,
one,
sir.
how is A
How is?
not join irreducible?
A is join
So in the first
irreducible.
one,
A is
A
join
is-
irreducible. A is
why,
join
sir?
irreducible. Because see, so okay, so if you take two other elements, 0 and A, okay.
So can't we take
so
0 and 0?
no. So can I write A is equal to join of X and Y? I have to write A as join of X and Y. So A, I can write it as join of only itself. There are only two elements. I can, and this is the maximum element. So A is equal to A join 0. Nothing else we can write. A is equal, so this
sir,
thing you see.
Sir, it says that A equal to X join Y implies A is X or A is Y. But if for all xy less than equal to A. So if we take 0 and 0, then 0 join 0 is 0. But A is not a 0.
But A is not of join, A is not equal to join of 0 and 0.
Okay, sir. Okay, I got it. Yes, sir.
Okay, let us look at the second thing. So B1. B, can I express B1 as join of two elements? What is B1? Join of which two elements?
B1 and 0.
0 and B1.
0 and B1. And so I think this implies that B1 equal to itself. So B1 is.
Sir, in the first statement, like not the alternate statement, A not equal to X join Y for X comma Y less than equal to A. So if I take both X and Y equal to A, then this doesn't hold, right? I mean, there's no restriction. We can't take them equal.
Yeah, maybe, yes, very good. We have to write that. So X is not equal to Y. X should not be equal to Y. Yeah, that should be included. Yeah, we'll update the slides.
Sir, X not equal to Y is still not sufficient because I think X not equal to A and Y not equal to A is required.
Sir, if X is equal to Y, then their join will be same also.
Yes, if either of them is A, then also it can be less than X comma Y less than A.
But why if one of them is A, one of them is A?
Then
yes.
Can be A.
Yes. In fact, you can see one thing, the alternate statement and the first statement are equivalent only under these two conditions. The alternated statement and the first one, if you don't assume that, then it does not hold.
Excuse me, sir.
Yeah.
So in the second diagram, A is not join irreducible, right?
A is not join. No, let us see. I have not yet reached that point. So is B1 join irreducible?
Yes, sir.
B1 join irreducible. Why?
Because only B1 join B1 and B1 join 0 gives B1.
Right. So these two are the only join that exists. Similarly for B2, is A join irreducible?
No, sir.
Why?
B1 join B2 is A.
Exactly. B1 join B2 is A. Not only B1 join A is A, not only B2 join A is A, but also B1 join B2 is A. So this violates the alternate condition. Does it violate the first condition? Let us see. Does it violate the first condition A? So B1, B2 are less than equal to A, fine. And A is not equal to join of B1, B2. No, that's not true. Okay, so the first condition is also violated. First condition is also violated. So A is not join irreducible. 0 is join irreducible. B1 is irreducible, B2 is irreducible, but A is not. What about the third lattice? Is C irreducible?
No, sir.
No, sir.
Why?
B1 join B2.
The join of B1 and
B1
B2
join
is
B2. Very good. A is it irreducible?
Yes, sir.
yes, sir.
A is irreducible. Similarly, B1, B2 are also irreducible. So can you mention what kind of structure should I, for an element, what kind of structure should I look at to decide if it is irreducible or not? What kind of structure should I look at?
If it has a branching in the lower half, then it is not irreducible.
Okay, let us come to this structure. Let us come to this structure. So in the first lattice, the power set lattice, can you tell what are the irreducible elements?
The four lower half elements.
The null A, B, and C. Are these the irreducible elements?
Yes, sir.
Yes, sir.
Yes, sir.
A, B, A, C, B, C. Are they irreducible?
No, sir.
No, sir.
Similarly, A, B, C is also not irreducible because you have multiple branches joining there. You have multiple branches. Okay, so I think formally you can say that. Okay, so if you AB, this is a join of. This is a join of. Oh no, this is a this is a join of which two? A and B. It's a join of A and B, and it is not equal to either A or B. So AB is a join of A and B, but it's a different element. So whereas if you look at null and A, A is irreducible because if you take the join of null and A, it's A itself. Or if you take the join of similarly null and A, it's null again. It's null. So 0, A and B, these are irreducible. Whereas anywhere above where you have two branches coming in, they are not irreducible. In the bit vector, what are the irreducible elements? Very easy. I mean, what are the irreducible elements? Okay, maybe I'm one-shooting the time. Okay, so 0, 0, 1, 0, 1, 0, 1, 0, 0. These are irreducible. Okay, I think thank you. We'll have other classes. Thank you. We will continue with this. We'll continue with some more definitions, and then we'll go. Thank you.
Thank you, sir.
Sir, the lab
Thank you,
class,
sir.
did it begin from 2 or 2:30?